Okay, all right. So what I was saying, table logic is so much easier because of the fact that you have very little time on the AP test. 90 seconds per multiple choice question. You don't have that many minutes on each section on the free response either. So it's something you've got to go quickly with, okay? So what you've got to do, there's some long directions down here, but we're not really going to, I'm not going to read those to you. You can read them yourself. We're just going to talk about how you do this. All right, so you have on your table, there are 5 experiments that were conducted. You have initial rate, you have initial concentration of A, and the initial concentration of B. You need to start with one experiment that the concentration of the other experiment is held constant. So you've got to compare 2 experiments. And if I'm looking at this, if I look at experiment 1 and experiment 3, the concentration of B is held constant. You see that? It's 0.2 for both of them. All right, so this is held constant. What happens between experiment 1 and 3 to A? It goes from 0.5 to 1. Is that doubling? All right, so that doubles 2 times. So then I have to look at experiment 1 and 3. What happens to my rate? Stays the same. No change. So if there is no change, what order is A going to be?
It should be first order. Right now.
No change. If you go back and look at your orders on the page before, the change in concentration of reactant has no effect on the rate. It is 0. So my A is 0. So if I'm looking at my rate equals K, my concentration at A is 0. So now we got to figure out B. All right, so we need to find where A is held constant. And if you look at experiment 1 and experiment 4, do you see how they are held the same? Okay, it's 0.5. So what happens to my concentration of B between experiment 1 and 2? Or 1 and 4, rather? It doubles. So then what happens to my rate between experiment 1 and 4? It doubles. So what order is B? Okay, look over here. If it is directly proportional, doubling the rate, the reaction, the concentration of the reactant doubles the rate, that means it's first order, right? So I'm going to say my concentration of B to the first power. If the question asked me to say, what are the orders for each concentration of each reactant? I'm just going to kind of go down here at the bottom. I would say it is what order with A? It is 0 order with respect or in respect to A. What is it with B?
First order.
First order in respect to B. And what is the overall order?
1.
Overall order is 1.
It's 1 plus 0.
Because 1 plus 0 is 1. How hard is that?
Not hard at all. I thought it was going to be a lot harder.
This part of kinetics, just talking about the rate law, is really not difficult. Now we are soon going to actually solve for some actual concentrations, but that is the beginning. Hi.
Want to take early?
Oh, that's fine. I've got a few more minutes and then we'll be done. All right, so the summary page. This takes what we just talked about in terms of the doubling and all of that and makes it a little bit more simplified. You can look at that. I'm not going to read it to you because you are capable of reading. But it goes over the rates again. 0, first, second, so that you can kind of look at that again. All right. Now, on the next page, it goes through the same reaction again. I'm not going to work that out again. It shows your summary reaction that we just worked out, that rate equals K times your concentration of A to the 0, B to the first. Can you simplify that? Do we need, what is A to the 0? 1. So really all it is K concentration of B to the first, right? That's all you have to worry about. So if you got this reaction rate and you actually had real numbers to put in this, and we can actually work those real numbers, and that's what you're fixing to do right now, that's all you have to worry about, okay? So right now what I want you to do, I want us to look at the first, we just need to pick an experiment, it really doesn't matter, but I want us to solve for K, okay? So K, if we rearrange it, is our rate divided by our concentration of B to the first power. Do you even have to write the 1? No. All right, so it's just rate over concentration of B. So if we look up here, and you can pick any of these numbers, it does not matter, just pick an experiment. Let's do the first one. So 0.5 times 10 to the minus second divided by my concentration of B. Well, concentration of B is 0.2. You do need to use your units, and the units are actually given to you in the table. So you got moles per liter times hour, and the concentration, what is that going to be? In molarity, or it could also be moles per liter. That way it would actually be in the same units as your rate, okay? Well, if you work this out, and it 0.5 times 10 to the minus second is actually 0.005, so it's actually here for you. Divided by 2, you get 0.025 per hour, okay? Because if you look at this, the moles per liter cancel, and you're left with per hour. So that is your K. And I'm not going to waste the time in doing it, but you could actually go back, and for every one of those experiments, you could calculate K for each of the experiments, and you would still get 0.025 for every one. All right? Now, a couple of examples. The ugly algebraic method, I'm going to let you look at that yourself. If you really want to do the math, that's how you do it. It makes a long equation. But you will still work out and still get your exponent, okay? It's just a longhand version. All right, look at exercise 2. You have this reaction. Your concentration of this very long is actually pentaamine cobalt chloride. Really long one. Plus water. They even give you your rate expression, that rate equals K times the concentration of that, but you've got to find out what this M is, what the exponent is, looking at the rate here. Only dealing with one concentration, so you just have to find one that you like. If you look at the first two experiments, what happens to my concentration? It doubles. If I look at the same two experiments, what happens to my rate? It also doubles. So what does that have to be then? It has to be first order. All right, so if we do our rate equals K times our concentration of this, and it actually should be in other brackets too. CO, because this is an ion, NH3Cl plus 2, and then the curly bracket, raised to the first power. So the concentration of all that. If I am going to solve for K, because it says, okay, find the value of M, we did that, calculate the value of K. K is equal to rate over our concentration, and to simplify things, and they really don't care if you do this on AP tests, you could just call that A. It's reactant A. Raised to the first power. Pick an experiment. I usually just go with the first one, just because it's easier, but you don't have to. Write down your rate, 1.3 times 10 to the minus 7, divided by your concentration, which is 1.0 times 10 to the minus 3rd. And you do need to be careful about your units, because this is moles per liter times minute this time. So your time is going to change a lot. Divided by, this is moles per liter. Okay. So moles per liter cancel. You're left with minutes. When you work that out, you should get 1.3 times 10 to the minus 4th per minute. Or, you know, you can write it as 1.3 times 10 to the minus 4th minute to the negative 1, if you want to keep it all in one line. That just doesn't seem natural to me. I like having it per minute as actually showing that underneath it. But either one of those is acceptable. Be sure, remember to circle your answer. Draw them an arrow saying, here is my answer. All right, exercise 3. This wants you to do several things. It says determine the orders for all 3 reactants, the overall reaction order, and the value of the rate constant. So you're supposed to find everything. All right? What's the value of K? And it also says what are the units of K. So you have to be careful about your units. All right, first thing you got to do, find 2 that are held constant. You've got 3 different ones here. So you've just got to actually find 2 of the concentrations that are held constant while another one changes. And this jumps out to me right here. If I look at the first 2 experiments, for bromine and hydrogen, those are held constant. What happens to my BrO3 though? It doubles. What happens? Okay, well, now we got to think about this. Look at our rate. You notice all of these rates are to the negative 3rd, but the first one is to the negative 4th. When you see that, if I were you, I would go ahead and change this and get it all in the same unit. Okay? That way you're comparing apples to apples and you don't have to stop and think about what that really means. So I would get, if you ever see that part of it is in a different form, go ahead and change them all to the same form. Make it easier on yourself. Okay, so if this is 0.8 and it goes to 1.6, what does that do? That doubles. So if this doubles and that doubles, what's my order here? First order. All right. For bromine, I now need to, and you can go ahead to make it simple on yourself. Go ahead as you find them and write it down. So that's first. We've got to find where this one and this one, so BrO3 minus and H plus, are held constant, and this one changes. So if I look at 3 and 4, those are the same, right? Stays the same, it stays the same. What happens to my bromine then? Doubles. What happens to my rate? It doubles. So what is my order for bromine? It's a 1 also. So my concentration of bromine raised to the first power. So now we got to find where these two are held constant. And this one changes. So if I look at experiment 1 and 4, that's constant. That's constant. What happens to that one? Doubles. What happens to my rate? Triples? Quadruples, right? 0.8 to 3.2, that's 4 times. This is the first time we've seen one of these. What does that mean that is? It has to be second order. So H plus to the second order. All right, so there's my orders for all 3. They might, on an AP test, again, they might expect you to say that the reaction is first order with respect to BrO3 minus. It would be first order with respect to Br minus. It would be second order with respect to H plus. So if it asks you, you need to write that out. If not, they may be just happy with you writing the rate expression. The second part of that, it says, okay, what is my overall order? 2 plus 1 plus 1? It is 4. That was hard. The next thing, the last thing it wants you to do, is to find K. Rate divided by, this is our concentration of BrO3 minus, raised to the 1 power, times my concentration of Br minus to the first power, times my concentration of H plus to the second power. Pick an experiment and substitute in. So I always, like I said, I just go with the easy one. 8.0 times 10 to the minus 4th is my rate. And remember, that's moles per liter times second. Divided by my concentration of BrO3, which is 0.1, times my concentration, which is 0.1, times the concentration of 0.1 squared. Remember your units. I didn't write them down, but this is moles per liter times moles per liter times moles per liter squared. When we get to figuring out our units in a second. All right, so if I work this out, it works out to be 8. And it is actually molarity cubed times second. All right, look at this. So we have moles per liter. One of those cancels with one of those down here. How many moles per liter do we still have? 3, which would be moles per liter cubed, or you could just say molarity cubed. And then you have to put your time second. All right, here is the shortcut. What is your overall order? 4. Your unit for molarity is always going to be 1 less than your overall order. So if your overall order is 4, then your molarity is just going to be 3. But it is cubed. You have to put it as a power. Molarity cubed. So if our overall order was 2, then it would just be molarity squared. Y'all get it? Whatever your overall order is, your unit is going to be 1 less than that. So if you have 4, take 1 finger away, you got 3. If it's 6, you had 6. For your overall order, take 1 away, you got 5. So it's going to be molarity cubed. Molarity to the 5th. Okay? So don't make it complicated on yourself. All right. That is the end of our notes for today.